next up we have Damian Steger, and he's going to talk about quantum computing. He's at ETH Zurich at the Theoretical Physics Lab, and working on a compiler for quantum systems. Also interested in high-performance computing, and also worked at the Google AI Lab, also working on the quantum computing project there in California. Thanks.
All right, thanks a lot for the introduction, and thanks a lot for the invitation to this, for me, a bit unusual conference. In the next 20 minutes, I want to give a really high-level view why I think quantum computers can actually solve some of the problems which CMOS cannot. Not all of them, but a few specific applications. So what is a quantum computer? A quantum computer is fundamentally based on different principles on how to process information. 100 years ago, we figured out that nature is not moving according to classical laws of physics, but quantum physics. Since then, we have seen many nice, interesting effects like quantum tunneling, entanglement, superpositions, to describe how atoms and electrons move. And so now a quantum computer is the first time where we try to use these laws of physics, not just to build devices, but to actually do information processing. All right, a quantum computer, at least a digital one I will explain here, has pretty much the same structure as a classical computer. You need to store your information. Instead of in bits, I call them quantum bits, or the short version qubits, and then you have to process them. You have to apply operations to them to get to your final result. So to start, you need to have something which is a zero state. And physicists like to write it like this, with this weird little notation, but that's just a zero. And you need a 1. And what I have shown here is, for example, a system where you have an atom and an electron. The electron can be in its lower shell with less energy, that would be a 0. It can be in an excited state, that would be a 1. So far I haven't shown anything different than classical computers where you have a bit which is either 0 or 1, either power or no power, however you want to encode it. However, if you build a computer which acts according to the laws of quantum mechanics, you can have a general state of your qubit, which is a superposition. And mathematically you would write it like this. But what that essentially means is that your qubit is not just a 0 or a 1. Sometimes, as people call it, it's a 0 and a 1 at the same time. And these alphas are actually complex numbers. So why don't we have good intuition how this works is because we never see superpositions in everyday life. Because there is a law of quantum mechanics which says that if you try to observe any quantum superposition, it has to collapse to the classical states, which are 0 and 1. And here you see with the probability given by this complex number squared. So in a sense, this equation describes you that your qubit is sort of in a probability 0 and with some probability 1, except that these probabilities can be negative or imaginary. And that's the puzzling thing why it's hard to think about them with everyday common intuition. So now you have 1 qubit, and you can write this state of 1 qubit as this nice formula with 2 complex numbers. That means you can store 2 complex numbers with infinite precision in 1 qubit. That's much more than you can do in 1 bit. In 1 bit you can either store a 0 or a 1. Here we can store 2 complex numbers. But the thing gets better. If you start scaling and you have 2 qubits in the same system, they can be in all possible classical states of 2 bits. So they can be in 0, 0, 0, 1, 1, 0, or 1, 1. That means you can store 4 complex numbers in it. Now, going this story further, if you have n qubits, you can store 2 to the n complex numbers. That's a huge amount of information. And now you can process this information. Similar, I would maybe call it quantum SIMD. You can make one operation, and you can manipulate all 2 to the n complex numbers at once. The only trouble is when you want to read out, you actually have to look at it, so you will only get one classical answer. But if you make a smart algorithm, it can make use of essentially doing 2 to the n operations in one go. So, are there qubits yet? Unfortunately, there are not yet large-scale quantum computers, but we already have a few different types of qubits. And I think every day I check, there are different proposals, but let me just mention 3 of them, which I think are currently worth mentioning. The best qubits currently are ion traps. These are essentially, you take an atom, you capture it, and then you use the electron to actually do the computation, like I've shown in the first picture. The good thing is, they live for about hours when they're isolated, One operation takes quite long, it takes like 10 microseconds, but the problem is you can only do currently 100 operations. So advantages for this technology is you can use single atoms, they're small, they're well isolated from the environment because you can put them in a vacuum. They're relatively slow to do computation and hard to scale beyond 20. That's something people are working on and probably solving, but that takes a few, well, maybe 1 or 2 years. The other type of qubits is probably superconducting qubits. This is on a semiconductor surface. You build superconducting loops, which essentially act as qubits. The currently best ones are about 10 from Google and IBM, and they have lifetimes which are very short, 100 microseconds. But you can do a gate operation in 10 nanoseconds. So one operation on 2 to the n complex numbers takes you 10 nanoseconds. So the advantage from this approach is probably that they're scalable because they're on a semiconductor surface. They're not single atoms you actually need to capture and put in a vacuum. But there are short lifetimes. However, in the recent years there have been much progress, so these qubits are actually good enough to be error corrected. So they're below a threshold where you can just add more of these qubits, we call them physical qubits, and with an error correction scheme you can make one logical qubit which lives longer than each individual physical qubit. So with this technology, when I'm later talking about one logical qubit to do operations, think of it as 10,000 small little qubits sitting on your chip, which need to be error corrected. And then the Microsoft approach, topological qubits, they go really a different direction. In 3 dimensions in physics, there are 2 kinds of particles, fermions and bosons. However, in the mathematical theory and in physics, you can predict that in 2 dimensions or 1 dimension, you can have different particles called anyons. And these have a very nice property when you do calculations with them. They're not located at one point in space, they're located at 2 points. So as here we have a wire, they will be located at the different ends of the wire, which essentially means that you cannot interact with them locally. So no noise from nature can just locally be on one side and change anything of your computation. So they will be much more error resistant. However, since 60 years they're looking for this Majorana, and probably they have evidence that they can show it next year, at least with enough evidence that the physics community accepts that these Majoranas exist. So let's go to the main topic, quantum computing beyond the exascale. And the question was, which I asked for this panel, is what are important applications that we can solve on a quantum computer, but you cannot solve on a special purpose post-exascale classical hardware we may build in 10 years. Anything classical you come up in 10 years. Usually I would explain small experiments we have shown in the lab, but if I want people to invest hundreds of millions in building this computer, I need to be better when I have that computer maybe in 10 years than anything you can come up classically. Because classical computing, we know how to go forward, and quantum is a huge risk to take. So let me go through a few of these algorithms. The most famous algorithm was 95 from Peter Shor, which showed how to solve the factoring problem. Here you see a number which is 768-bit. And the problem is, can you find its 2 prime factors? This was actually done in classical CMOS, 2009. It takes 2,000 CPU years. And then you get the solution. Well, this scales exponentially on all classical hardware we know. We can't prove that it has to scale exponentially, but for all algorithms we know it does. However, we know that on a quantum computer, there is an algorithm called Shor's algorithm, which can solve this problem in polynomial time. And you only need 2n plus 3 qubits, which is a small number, and you can solve this problem. So, why is that useful? RSA encryption is based on the fact that you cannot factor numbers, large integers. And as you can see for the CPUs, it took 2,000 CPU years to crack the 768-bit code, and it would take thousands and millions of years to actually crack the codes you're currently using. A quantum computer can do that in hours with 2n plus 3 qubits. If you give me linearly amount more qubits, I can do that in seconds. That's why a lot of funding came into the field of quantum computing, simply because the US government is interested in actually cracking RSA encryptions. Even though it's the most famous algorithm, I'm not particularly a fan of it. Why? Because it's not useful. Why isn't it useful? Well, there are even books written on something which is called post-quantum encryption. Once I know someone has a quantum computer, I can switch my encryption scheme. I can either go to quantum encryption, where I need completely new devices and a new infrastructure, or even easier, I can go to lattice-based cryptography or other classical encryption schemes, which are not based on factoring, and then my quantum computer is useless to try and crack it. It will at most give me a square root speedup, and that's really not useful. So let me go to the killer application for quantum computers. First, here is some old data when I looked at which applications run at scale on today's supercomputers. And I can say probably a fair amount is simulation of quantum systems. Is that material science, chemistry, condensed matter physics? These are, first of all, important problems to solve, and secondly, of economic impact. So the question is, can a quantum computer actually do something for these problems? And that's actually where the first quantum computer was proposed by the Nobel laureate Richard Feynman, who said in '82, solving a quantum system is easiest if you have quantum resources. Why is that? For people who are working in the field, if you have a chemical system or something which behaves quantum mechanically, you have a wave function which says in which state the system is. This wave function has 2 to the n complex numbers depending on the number of particles or orbitals you're considering. Now on a classical computer, to store 2 to the n complex numbers is very hard. On a quantum computer, I need only n bits, because n bits can represent 2 to the n complex numbers. That's one of the bases why a quantum computer is very good for them. And here is my young wish list of things I actually want to do. Room temperature superconductors, catalyst for carbon sequestration, solve global warming, and catalyst for nitrogen fixation. Nice topics. I will show one of them, how you actually can do it. The nice thing about these problems from a quantum computing perspective is that these problems are hard for classical computers. You need high accuracy to actually get the solutions, and you cannot achieve them with any of our approximate classical algorithms. Monte Carlo won't work it, DMRG, and whatever else, DFT. And to achieve more accuracy, it would be exponentially hard classically. But these algorithms scale polynomially for a quantum computer. And that's usually the point where people stopped in the quantum information theory groups, which said, okay, we have an algorithm, it scales polynomially, we're done, we're better than classical computers. And only in the recent years, actually people started looking at what it actually takes. Scaling an algorithm better, yeah, I know, could be good, but the prefactors matter. So 3 years ago, a group from ETH and Microsoft looked at a small problem which is just large enough such that in 10 years you won't be able to solve it on an exascale machine. Just here are the numbers. If you consider quantum chemistry, you need spin orbitals. Like for my wish cuprate high temperature superconductor, you need probably 10,000 orbitals. For interesting chemical reactions, 200 to 400. What we can classically do is probably 70. And this is just like the scale, like how accurate we need to have it. So, these quantum algorithms essentially scale with the number of spin orbitals you look at. If you want to have 200 spin orbitals, I need 200 qubits. Classically, you need to store 2 to the 200 complex numbers, which would be larger than a larger number than there are particles in the universe. But on a quantum computer, that's easy. So they looked at one molecule and actually calculated. You can only do discrete sets of operation. You have an architecture which is planar, and you need to do error correction. And for these tiny little molecules, they came out with a gate count of 10 to the 18. Well, that is very bad. I mean, yes, it scales polynomially, it's better than exponential, but 10 to the 18, I'm sorry, that's not going to happen. Especially having a quantum computer work for 30 years. And you can't stop the calculation. Because as soon as you look at it, you would destroy it. So you would have to have a quantum computer working for 30 years non-stop. Well, that's not going to work. So there were a series of papers in the recent 2 years coming out to improve the algorithms, actually looking at what I would call high-performance quantum computing, improving these algorithms, especially the constant factors, and they came down to 2 minutes. In the recent year, probably we have another order of magnitude reduction, but now I think this problem we can solve on a quantum computer. But still, the next question we asked was, can we get money for it? Because that takes a few hundred millions to actually build such a quantum computer. And I'm not sure if you can go Monday morning into your boss office and pitch for having 100 millions for saying, I can solve this molecule, I actually don't even know what it's useful for, but we can't do it classically. So that's why I'm really thrilled to actually show the next application, which was published a few weeks ago. Let's look at an actual application which has economic benefit and impact, and which we might be able to solve on a small-scale quantum computer. And that's nitrogen fixation. The problem is simple. You need to have fertilizers for your plants to grow, to produce enough food to sustain humanity. Well, you need to turn nitrogen from the air into ammonia, and preferably at room temperature, and with as least energy as possible. The only way we know how to get this done is by a 100-year-old process from Haber-Bosch, which essentially requires high pressures and high temperatures to produce this fertilizer. That takes about 3 to 5% of the world's natural gas consumption and 1 to 3% of the world's annual energy consumption from humanity. That's a huge energy cost. But we know there is a better solution, because before the Haber-Bosch process was invented, we also had fertilizers. Well, simple, bacteria in soil can do that. And bacteria in soil don't have high pressures or high temperatures. They have an effective catalyst to actually do this reaction at sufficient high rates. Currently, chemists are struggling to actually synthesize such a catalyst. They have a few, but they're working very poorly. And all classical methods to actually compute how the reaction has to work, to construct a better catalyst, fail completely because it's exponentially hard. So that's a task where this paper, which was published by 2 groups from ETH and Microsoft, tried to figure out how much would it take on a quantum computer. Not just taking an abstract scaling of an algorithm, taking a specific architecture, compiling it down for these operations you can do, adding the error correction, and also see how you can do parallelism, all kinds of different architectures. What they came out in the end is that you can design such a catalyst because you can calculate the energy sufficiently enough, and so imitate what the bacteria are doing. And you can do that with a small quantum computer. And with small, I mean a quantum computer with on the order of size where you can factor a 4,000-bit number. That's about the size which the NSA wants to build to crack RSA encryption, but that doesn't really have use for pretty much everyone except them. And here they have shown that nitrogen fixation, you can solve this problem with the same size of a quantum computer. So currently we're at the stage where we want to look at what can a quantum computer do, but we want to find killer applications, not just better scaling algorithms, but problems we can actually compile it down and count how many resources we need, how many qubits, how many operations. That is a very hard challenge, first of all because of the HPC community. Every time I come up with a problem, it has to be hard enough that it cannot be solved on an exascale machine, because otherwise, better build an exascale machine. Then, the problem has to be amendable to quantum acceleration. We only know of a handful of algorithms which have a scaling advantage compared to classical. A quantum computer can technically do any calculation you can do with classical architecture, but it won't be faster, it won't be scaling much more. And the error correction overhead will probably make it not really affordable. So we have to find a good algorithm. And then the crossover scale has to be short enough. And this is something I have encountered many times, where the algorithm scales better, the prefactor is 10 to the 27. Well, not really good, right? So potential applications I've shown here is factoring for code breaking. If you're one of the government agencies, that's probably a good thing. But more importantly is quantum chemistry and material simulations. They're extremely challenging. You have to spend years on optimizing algorithms, and then obviously to build a large-scale quantum computer with enough qubits. But that is probably worth investing in. I haven't looked at other applications due to time, which is quantum machine learning. There are algorithms which scale better for machine learning and artificial intelligence on a quantum computer. Why haven't I looked at it? First of all, time. Secondly, usually the amount of data you need to feed is quite large. So you're not talking about a small-scale quantum computer, you're talking about medium size. And also solving linear systems. There is a beautiful algorithm under a few assumptions. Say you only want to have logarithmic bits of your answer vector, or complex numbers. You can solve a linear system in logarithmic time. Fantastic. The question is, do we have small enough applications where this is hard? Probably not, because linear systems we can solve on classical computers fast enough, until probably they grow to a huge size, but then we also need quite a medium-sized quantum computer to solve. So with that, I'm at the end, and I'd like to thank my collaborator and the audience here for your attention.